Our world is full of diagrams, graphic representations of everything from the solar system to the hidden origins of life. They have a unique ability to express complex ideas simply, and an intellectual and artistic beauty that has the power to inspire awe and change our perceptions. Diagrams can exert a wonderful and unpredictable influence in the arts as well as in science. These extraordinary displays of light and colour wouldn't have been possible without one of the greatest diagrams in the history of science. In 1664, Isaac Newton bought one of these at a country fair near Cambridge. Using a prism like this, he embarked on a series of experiments that would answer a problem that had challenged scientists for generations: the nature of light itself. And here is the vital document, Newton's hand-drawn diagram, which shows us exactly how he did it. Newton went back to the basics. What exactly is light? What is colour? His ideas didn't just transform our knowledge of what we see, they revolutionised how we communicate. And the prism and its rainbow colours have become a captivating artistic image. So how did Newton discover the real properties of light? And how did his work become a huge influence on centuries of science and art? Newton's light spectrum is so well known today that children can rattle it off in the classroom.
Red, orange, yellow, green, blue, indigo and violet.
But 400 years ago, much less was known about light and colour. Scientists couldn't work out how colour was produced. They thought white sunlight was pure, and that colours must be a modification of it. Then, in 1666, at the height of the Great Plague, Isaac Newton started conducting experiments with prisms that would unveil the secrets of light. As it happens, the diagram that Isaac Newton drew is kept here in my college in Oxford, New College. Now, I've never seen the diagram, but I'm told it's a rough sketch that Newton made with pen and ink on a scrap of paper he was keeping notes on. The notes weren't about light. They weren't even, in fact, about science. They were notes on theology and his thoughts about the Old Testament. Sounds familiar. My breakthroughs are usually penned on the back of old envelopes. In a very dark chamber, at a round hole, about 1/3 part of an inch broad, I placed a glass prism, whereby the beam of the sun's light, which came in at that hole, might be refracted upwards towards the opposite wall of the chamber, and there form a coloured image of the sun. And this is the book which contains that vital diagram. It's a book of notes which date back to things he wrote at the beginning of the 18th century. And you can see he doesn't waste any of the paper. Paper was very valuable at the time. And somewhere here should be the diagram we're looking for. Ah, there it is. Beautiful. It's called The Crucial Experiment. Rather sketchily drawn, looks a bit hurried. But this simple diagram is a pivotal image in scientific history. A graphic moment when the ancient world was overturned by modern science. What Newton shows us is his room here with two prisms, one on a stand and one on the table. Now, there's a source of sunlight here which comes through a small hole through the shutter, and then it's focused by this lens and passed through the prism on the table. Now, this is where the magic happens. The white light passes through the prism and then is split or refracted into its constituent colours, which are then projected onto a little board that Newton's drawn at the back here. Today, we sort of think of the spectrum made up of 7 colours, but Newton wasn't quite sure about that. Sometimes he wrote about 5 colours, 6, sometimes 7. In this little diagram, he's drawn 5 colours. So far, so good. But what if you take one of those individual colours and shine that through a second prism? Does that get split up into even more colours? This then was the second part of Newton's crucial experiment. The diagram shows us that the board here has a hole in it, and by moving the first prism, Newton could direct a single colour through another prism behind the board. The colour that passes through the second prism does not change colour. Red stays red, blue stays blue. Newton has discovered a fundamental law of nature, and he writes it out here in Latin: nec variat lux fracta colerem. Refracted light does not change colour. This diagram proves that the colours in white light, the colours that we see in the rainbow, are immutable. And amazingly, over 300 years later, the crucial experiment depicted in Newton's diagram has made possible further huge scientific discoveries that have been seen not only in science, but in beautiful light art shows like these. In the 1940s, Newton's work led to the isolation of laser light and the development of holography. These holograms were produced in the 1980s by the first artist-in-residence of the Royal Greenwich Observatory.
We found our inspiration in the library, looking at an early edition, first edition of Newton's Optics. What he was looking at and what he was trying to observe, but he couldn't define, was kind of an interference pattern. And interference is absolutely fundamental to the hologram and making a hologram. So that kind of made us feel that was a language, a kind of similarity between the optics of Newton and the kind of modern technological hologram.
Do you think Newton would have enjoyed the games that you've been doing with light?
Yeah, I hope so. This hologram is accurately representing, for example, the colour blue, which is almost impossible to do in pigments or dyes. But we've got interference light here, so we've got really pure blue.
We're taking what we find in a textbook and making it more magical. Somehow the language of physics, for example, can somehow destroy the beauty of the phenomenon that the scientist is observing. So in a way, I think as artists, we can put a little bit of that kind of magical, just aesthetics back into a textbook diagram.
So why was understanding light so important to Newton? One answer is because no one else had. Newton stood in a long line of scientists who had tried to explain how light happened. He realised that it was only because of light that we can see and examine nature. So he wanted to investigate the medium that made all other scientific endeavour possible.
Newton studied the traditional Aristotelian curriculum, which had been studied for about 300, 400 years. And then at some point in about 1664, so 2.5 years after he went to Cambridge, he suddenly gave it all up. And he started attending the lectures of the first Lucasian professor of mathematics, Isaac Barrow. And there he was exposed to the most advanced mathematics of its kind in Europe. And there's some very interesting material in his manuscripts which suggests that he's very interested in finding out how much the mind controls what we see.
Newton's decision to investigate the subject of light coincided with a nationwide epidemic that would drive him out of the university and back to his home in Lincolnshire. Plague had ravaged London and was beginning to spread across the country. As one college record put it, "It has pleased Almighty God to visit the town of Cambridge with a plague of pestilence." Newton had to flee Cambridge, and he came back here to Woolsthorpe Manor. This was his family home, the place where he'd grown up and entertained himself by making sundials and model windmills. And he was now about to embark on some of the most important experiments of his career. It's said that Newton loved apples, and over there is the direct descendant of the tree that Newton reputedly sat under when the apple hit him on the head and he grasped the full significance of gravity. This is also where Newton discovered one of the most important topics in my subject, the calculus, which helps you to calculate the changing speed of an apple as it flies through the air. At Woolsthorpe, Isaac Newton's work on gravity, calculus and light would turn him into the architect of all future science. He believed passionately that the real truth about light and colour had yet to be found, and he went to extraordinary lengths to discover it. Some of his experiments were really dangerous. On one occasion, he slid a bodkin like this, a large flat needle, betwixt my eye and the bone, as near to the backside of my eye as possible. Not for the squeamish, this. But what it did was to alter the curvature of the retina, and the more that he pushed, the more rings of colour he saw. The light was refracting as he manipulated his eye. This mad obsession arose out of Newton's conviction that there was, as you might say, more to light than met the eye.
Hello.
To understand how Newton did his prism experiment, and about just how important it still is, I've joined research scientist Kate Lancaster.
Yeah, so he used the sun as a light source, and the sun sprays light in all directions, and you need a parallel beam for this experiment to work. So what Newton did was he used a lens to collimate the light, i.e. make it parallel. But we're going to use a slit.
Okay.
Our source is far away, so what the slit does is basically limit us to the rays that are just going in one direction. The resulting parallel beam of light, we then put through a prism, just as Newton did, and we can see on the wall
Oh yes, okay,
that the spectrum has appeared. The parallel beam of light is passing through this prism and goes through a process called refraction, which is essentially bending the light. And each colour that makes up the white light is actually refracted different amounts. So hence why the light is actually being able to be dispersed into its different colours. Some people argued that actually the prism did the colouring, but Newton actually devised a second part to this experiment which showed that this wasn't the case. He actually used a second slit to select one colour. So I'm going to select red. Then I put a second prism in, and basically what we've done is we're refracting that red light. It's not been further coloured, it's just been further refracted by the second prism. So this was, to Newton, the definitive experiment which showed that, number one, white light was made up of multiple colours, but number two, it wasn't the prism that was colouring the light at all.
So why is this experiment important?
Well, I mean, it was the first time people realised that white light was actually made up of multiple colours. And that information almost certainly influenced people like James Clerk Maxwell, who was a scientist at the end of the 19th century, in his discovery of the entire electromagnetic spectrum. You know,
so there are things
ranges
beyond
from,
the blue
you know,
and the red on either
things you
side
can't
which we
see,
can't see.
microwaves, radio waves, all the way up to hard X-rays and gamma rays. Without the knowledge of the electromagnetic spectrum, we wouldn't have modern communications. So it would be a really silent world without the knowledge of this EM spectrum. So this tiny, small, simple experiment just has a massive impact in our lives.
Gave us the first inkling of what really is out there.
Absolutely.
Yeah.
Newton's way of doing things combines something that can be drawn. It's very important for Newton that you can see things. The drawings we have of his work in the late 1660s, that they show a great obsession with precision. And that marks out his mathematics and indeed his science thereafter.
On Newton's return to Cambridge, he began refining his theories. Scientists have been investigating the properties of light for 2,000 years. They knew that light travels in straight lines, and that we see objects because of light rays bouncing off them. The Roman mathematician Ptolemy had noticed that light bends when it enters glass or water. And as Newton took up residence again at Trinity, over in Italy, Galileo was busy working out the speed at which light reaches us from the sun. What made Newton different was that no one agreed with him.
The theory that he's putting forward is so incredibly unusual. He is saying that white light is composed of a number of primary coloured rays that are brought together. Everybody else says that colours are confused modifications of white light. Everybody else is wrong.
I think you can see the tension between Newton's radically new thinking and the accepted science of the period in another of his diagrams. It's called the colour wheel, and it appears in Book 1 of Optics. This is a first edition, and it dates back to 1704. But the ideas it contains were discovered some 30 years earlier. And here's the wheel. What Newton expected when he refracted white light through a prism is that it would come out looking like this, like a wheel. It's what most people thought at the time. The fact that Newton drew this diagram is somehow echoing that old thought. His spectrum has 7 colours this time, unlike the 5 he had in the prisms diagram. Many experts think he was keen on 7 because it would marry light to other harmonious features of the universe, such as the musical notes of an octave, which he marks next to each colour. The colours complement each other as you move around the wheel, until eventually violet shades into red. It's a little bit like the idea of a musical scale. If I start on the note C, I end on a note which sounds remarkably like the note I started with, which we also call a C. Everything about this image really harks back to the idea of a divine order. So, if Newton had solved the mystery of light, what were the implications? Was it just a theoretical abstract breakthrough, or were there practical uses? Well, in 1668, Newton turned his attention to trying to design a new telescope. He realised that the breakthroughs he'd made on light and glass could help him to solve a problem that had dogged astronomers across the world. The scientific revolution of the mid-1600s had depended on refracting telescopes, the kind Galileo used to survey the stars. But they had a problem with chromatic aberration. As light hit the lens, it refracted, creating a blur of colour. For Newton, light was the key to seeing into nature. An accurate telescope was essential. He decided to create a reflecting telescope with mirrors. Tucked away in his rooms here in Trinity, he ground the mirrors using a new alloy he'd invented. He'd made the case and the mount. The thing was scarcely 6 inches long, yet it had a magnification of 40 times its diameter. The equivalent refracting telescope at the time was some 6 feet long. Newton's grasp of refraction, so brilliantly captured in his diagram, was the key to achieving the perfect telescope. This is the Orion Optics factory, the only company in Britain that produces top-class telescopes from scratch, including the Europa 150 Newtonian telescope, a direct descendant of what Newton made in the 1660s. Newton found that a well-made mirror at one end reflected a perfect image to a second mirror angled to face the eyepiece. People said that single-handedly he'd revolutionised the science of optics. He was well on his way to becoming the country's leading scientist and an acknowledged genius at 28. But Newton has had his critics as well. The poet John Keats felt that Newton had reduced the beauty of light to a mere event, created by particles. A cold philosophy, he called it, that would unweave the rainbow. But there's an irony here. Artists have frequently used Newton's scientific diagram as the inspiration for art. It's hard to imagine, but there is a connection between Isaac Newton and Pink Floyd. In 1973, the Prism was the key idea behind one of the most visually exciting album covers in the history of rock music. Dark Side of the Moon. The cover's designer was Storm Thorgerson.
It was related to Pink Floyd's light show, and we were also responding to the keyboard player, the late Rick Wright, who said, "Let's not have one of your pictures, Storm." And he said, "Why not some cool graphic?" Newton was not in our minds particularly. I think I had originally seen a textbook drawing, which is very straightforward, much like this, but only in black and white. I thought, well, that's quite nice. I mean, we're not scientists. It's the graphic rather than the science that makes it strong, and the triangle is part of that graphic. And I think that the graphic allows you to screw with it, allows you to mess around without, as it were, altering its integrity. Behind me here is the stained glass window, which I much prefer, which is also cute, is that the word? Nifty, because it's rendered in something that is about light, namely glass. And its subject is about light, because it's the prism and spectrum, but it is very clearly dark side of the moon. If you get it when the sun's shining through it, it's beautiful. I recommend it to anybody who has a private chapel.
So you think if you showed somebody that, they might think Pink Floyd before they thought Newton?
I think they would definitely think Pink Floyd before Newton. I suspect Pink Floyd in this contemporary age are probably a little more well-known.
Pink Floyd's album cover makes it seem that there is in nature a band of distinctive colours. They appear as separated. Each has a name. But what are we actually seeing when we identify colour? Is the way the brain perceives light as important as the light itself? And is it entirely accurate to give colours different and separate names? Newton believed that the properties of light meant that each wavelength corresponded to an individual colour. But is that considered scientifically accurate today? I'm visiting Bo Lotto in North London. He's a scientist whose specialist study is the perception of colour.
Colour doesn't in fact exist outside the brain. The brain makes it all up. Colour is purely a function of the brain. Newton showed us that you can take white light and you can break that into different wavelengths, but I can take any one of those wavelengths and I can cause you to see it in lots of different ways. So here, what I want you to notice is that you have an outline drawing of two cubes.
Yeah, yes? Kind of mega Rubik's cubes.
Yeah.
Like.
The one on the left has 4 grey tiles.
Yeah.
And the one on the right has 7 grey tiles.
Yeah.
Okay? They're all the same grey.
But are you saying you could mess with my mind to such an extent that I would call that actually a completely different colour?
Yes. I'm not going to change the physical quality of those surfaces at all. Okay?
Right.
So tell me what happens to your perception when I reveal these two scenes.
Whoa, it's changed to blue.
And what you're seeing there now is the two scenes as if they're under different conditions of illumination, under different lights. The 4 blue tiles are all grey on the left.
Okay.
And
Am I
they're
gonna move
all
over
the
here, was
same
it?
as the 7 yellow tiles on the right. They're all grey.
Oh no.
What Bo has done is to throw a differently coloured light over the cube, except where it's grey. That ambient light alters my perception of the grey tiles.
That's your physical reality.
Yeah.
Right? All the things are physically grey, but that's your perceptual
Whoa.
reality.
I would have said there were 3 different colours there, and you're saying there's really only one wavelength of colour.
There's one wavelength, right? But I can get you to see that wavelength in lots of different colours.
I mean, does this make some sort of nonsense then of what Newton was, he argued about maybe the 5, 6, 7 colours in the spectrum, but in some sense, does that not make any sense then?
What he was really demonstrating is the physicality of light, right? Which was, of course, tremendously important. But what he wasn't talking about necessarily was the perception of light. So the reason why you see that as blue there is because in your past experience, a grey light coming under yellow light would in fact have meant a blue surface, just the laws of physics. So that's why you're seeing it as blue, because it would have been useful to see it that way.
I'm kind of intrigued to see what colour my top's going to be tomorrow morning after all this.
"300 years after Newton drew his diagram to explain his theory of light to the world, it still reaches down through history and touches even a brand new science like cognitive behaviour. And by revealing the real properties of light and colour, Newton made it possible to develop fibre optics, laser technology and holography. It's these wider scientific and artistic consequences that confirm the enormity of what this great man did when he sketched out his crucial experiment on a scrap of notepaper. It's amazing to realise how much Newton understood about light from such simple experiments. He buys a prism in a country fair, sets up an experiment in his bedroom, and suddenly the mysteries of light are revealed. The genius of Newton is to look at nature through the prism of mathematics. Geometry, the lines and angles that he drew inside that diagram, are what gave him the insights into the mystery of light and colour. That diagram, the little hand-drawn sketch that he drew on a scrap of paper, not only revolutionised scientific thinking, it also gave us an unforgettable image of enduring beauty.